Come back to the third talk of fourth day by Dr. Animesh Kumar Sahu, titled Control and Operation of Solar PV Powered Hydrogen Systems. Over to sir.
What I am going to discuss in this lecture, of course, I will not take much time because we are heading to lunch and we are already late, but still I will give a overview of this concept because just before this, you know that one of the renewable significant renewable energy we can use to produce the electricity, which is wind energy, right. Then when you say renewables after wind, what it comes to our mind also solar PV, right. Now again before I start, I will ask one question. So what is the solar PV output and what is the input for electrolyzer? DC, right. And so but in wind what you saw, like you generate AC and then you have this extra rectifier stage to bring down the AC generation to DC, right. And again also here also I can say it can operate in both mode. Let us say you are only focusing on DC grid or DC microgrid, there you may not be need because all your generation and loads will be DC. Okay. But some application, let us say you have a big solar power plant where you are going to use some hydrogen electrolyzer in the existing solar power plant in the megawatt scale, and the solar power plant is already connected to AC grid, and in a common bus you want to connect a hydrogen electrolyzer load. So that time you might need a rectification stage because you are bringing the power from the AC grid. Okay. So in this talk that we are going to discuss. So I will discuss a brief of introduction and a overall system architecture, okay, how a solar PV power fed electrolysis can happen. Then topologies, what are the topologies? When I say topology, maybe I am mostly talking about the power electronic topology, what can be involved in those process solar PV power fed electrolysis. Then MPPT control method, as all of you know, I know, but I will just give a brief, like some people asked in the previous session how this MPPT is a theoretical or mathematical. So what are the processes involved and why it is called maximum power point tracking? It applicable to both solar and wind, and in solar perspective I will discuss here. Apart from that, as we told, it is a DC grid or whether you are taking from AC grids, because hydrogen electrolyzer yesterday and from beginning we know it is a low voltage high current device. So whatever DC you generate, sometimes depending upon the architecture you are going to use in the process, you might need some kind of DC-DC stage in between, whether it is a DC-DC boost for the solar PV generation or might be a DC-DC buck at the end side for the electrolyzer, hydrogen electrolyzer. Okay. And if time permits, I will tell about two types of case studies where I will consider how you can do some kind of system level analysis when you have solar PV and hydrogen electrolyzer in the system. Okay. So this is one of the again statistics. So you can see the globally hydrogen consumption rate, it is of course till 2020. You can get the information from the given references. So the radius of the circle tells you how much is the magnitude of the amount of hydrogen is being consumed in the different country of the globe. Okay. So the more the radius, more is the consumption. That is how it is represented here. So if you see, China is the highest consumer for the hydrogen electrolyzer globally, and this list is till this the data or the statistics is till 2020. So if you want to know updated thing, you can search, but this is collected from the source I mentioned. So that means by 2020 itself, all over the globe people are aware of this hydrogen electrolyzer consumption. That means, and now to consume something you need to generate hydrogen first, and that is why we are coming up with whether different types of hydrogen production, which already we discussed. So one of the technique is green hydrogen, where we use some kind of renewables, whether is wind or solar, to generate this hydrogen production. So, now as I told, our India also itself is targeting almost 500 gigawatt of non fossil fuel based power generation by 2030. So, to accommodate all huge amount of renewable energy source, also India has a mission called National Hydrogen Mission. In that, they are also targeting to generate more and more hydrogen by 2030. So, that because it is a storage like battery. So, once you have a more renewables, you can definitely predict the power generation profile will be very much fluctuant. If you remember some of the previous slides of Professor Jahangir, once you have more renewables, your power demand and the generation profile itself not very smooth. And to mitigate that, we have a concept called demand flexibility, where mostly battery we use, but in upcoming generation we are going to use hydrogen energy storage. So, to accommodate more and more energy, renewable energy, we are coming up with more and more hydrogen, and all, not only us, all over the globe you can see it is almost fair distribution of consumption. Okay. Now, why we require PV based green power, green hydrogen? Because it is the first global push of carbon neutrality. It is a very generic statement. I mean, it is not only applicable to solar PV, it is applicable to all kind of green energy which does not emit any kind of greenhouse gases, right. And then from that we also know that this hydrogen is a clean and storable energy sector, and PV driven technology, of course, as solar PV is involved and you do not emit any kind of greenhouse gas, and also it is scalable. You can have a solar PV power fed electrolyzer at a distributed level, which you can call microgrid level. And when you talk about the grid scale hydrogen integration also, there also you will have other resources. So, you can build megawatt scale level, and of course, when you go for that megawatt scale level and connect to grid, definitely you can help in some kind of grid ancillary services. So, that is why that becomes a scalable technology. It is scalable from the kilowatt level to megawatt power level. Okay. Depending on application, you can use that. I am doing this. Again, this is a sketch of the solar irradiance distribution, and if you see, the scale is basically a radiation curve, a radiation scale. And if you can see, based on the geographical location where we get the more and more solar irradiation. Okay. And mostly if you see, it is more and more red. So, the radiation I mean measured in terms of kilowatt hour per meter square is more. Okay. So, here I can see mostly some part of Australia. If you see, this is the Australia and some part of Africa. You have the high radiation, and the lowest radiation you find mostly in the American region. Okay. So, what we can do here? So, basically we integrate the electrical and electrochemical subsystem, right, because solar again energy it produces electrical energy, but the consumption from the load perspective, load is basically electrochemical load, right, what we discussed, the electrochemical equivalent. So, depending upon that, so it basically combines that electrical energy to produce some electrochemical load, and also you have to properly model it to get high efficiency. Okay. So, you are getting solar irradiation and generating solar power, but your power transfer to the electrolyzer should be highly efficient, whether you are using through AC to DC stages, multiple DC conversion, or you are using directly solar coupled DC. So, that converters or the total solar hydrogen electrolyzer membrane, all these things should be properly designed, so that when you whatever the generated energy should be highly efficient when it reaches to the hydrogen production. So, that hydrogen production will be also good. Then we will see, as I told, overall system architecture. So, here I am showing a solar PV power fed electrolyzer model, and in that what are the parts involved in the first solar PV model. Okay. As you know, two factors generally mostly affect the solar power generation, one is irradiance and the ambient temperature. Okay. So, those two are the most governing parameter how your solar power generation profile looks like, and that depends on electrical power also of course. Then again, when I say solar, if it is a kilowatt level or megawatt level, it is not a single solar PV panel. You will have so many PV panel, like we discussed. For electrolyzer, it is not a single cell that can give you the required amount of power. So, single cell, if you see VI characteristics, the cell voltage is very low in the top form of 1.9 to 2.2 volt, but you have to again make it series connection and to make it a low voltage and high current device. Similarly, solar PV panel, depending upon how much power and how much particularly voltage and how much current you want at the output. Similarly, panels can be arranged in series, parallel, or both series and parallel combination, or you can also arrange these solar panels, solar inverters as centralized or central inverter or string inverter you can use. So, depending upon you want to generate centralized solar or distributed solar. Okay. Now, as you know, solar power output is basically a DC, right, and the DC-DC converter model here I showed. Sometimes depending upon if you want to, sometimes for grid connection of solar you need a boost converter, because the solar voltage output voltage that you generate from the DC exactly from the solar PV panel is not compatible with the grid scale DC link voltage. So, you need a step up operation. So, you basic structure is a single stage boost converter you can use, and you can achieve the same achieve the voltage whatever the input from the solar, and the output will be a grid level inverter DC link voltage thing. Okay. And here again what I am saying, sometimes in the next slide I will tell there are different types of architectures for this solar PV power fed electrolyzer, but in this what I mean to say, in case you are using a DC-DC buck converter. So, if your solar voltage is already sufficient, you do not need, but if your solar output voltage is not sufficient, maybe you have some kind of DC-DC boost, or maybe if you want to reduce to the electrolyzer level voltage, you make it a DC-DC buck converter. Okay. And in that already we discussed DC-DC converters objective when you go for converter design or controller design. So, these are the objectives, mostly the conversion ratio. We require a high voltage conversion, because if you are generating a high DC but the electrolyzer needs a low voltage DC, you have a you should design a converter that can step down the voltage with a high conversion ratio. Then also you have to properly design a controller, what I told, that controller will take care of your current ripple that can be found at the output of your DC-DC converter, because that high, if you supply high amount of ripple current to the hydrogen production, then it will be less efficient. So, the controller objective also should be properly taken care of. Okay. And apart from that, efficiency. So, basically current ripple also somehow related to your efficiency, because if your input power to the DC-DC buck converter is not properly transferred to the electrolyzer input, then the efficiency will not be good and your hydrogen production will be not up to the required amount. Okay. Because hydrogen production, it totally depends how much power or current you are giving to the electrolyzer. You saw the electrical equivalent, the current decides all the kinds of over potential, right. If that current does not go to the electrolyzer proper amount, all the over potential will be less, and your hydrogen power, output power or hydrogen production in terms of whatever quantity you use, that you may not get. So, the power supply should be proper. And electrolyzer model also we discussed everything. So, mostly different types of equivalent circuit we discussed, so we can use here also static model, dynamic, electrical with considering sometimes concentration over potential or avoid it, or sometimes electrochemical model where you try to emulate all the chemical reaction in terms of electrical equivalent and then model it. And Yeah, so there are other models also there, thermodynamic model and all. So this is basically a structure where you generate the solar from the solar power from the solar energy, solar PV, and then you fed directly to the electrolysis. Okay. There is no grid concern here. So this is a very generic architecture. So this is actually I will refer a very good paper. So it will give you a very good brush up of knowledge about the solar PV power fed hydrogen electrolyzer. Okay. Now this is, I think most of you know and some of you may not know. So this is how we model a photovoltaic model, right, solar PV model. So how many are acquainted with this equivalent circuit? Backside students, are you seeing first time, right? Okay, so there are other equivalent models out there, but this is a very simple model to understand. So if you see there are different current and resistances I mentioned here in term to represent a equivalent photovoltaic model. Okay. And the IL, what is coming from the source, that I called as a photo current. So basically solar cells, what they do, they absorb the radiation and convert into electrical energy. So that photo current IL I represent, and there is a parallel diode, current diode is also there. So you know the current through the diode is not linear, right. So that diode current expression is provided in equation number 2. So it's basically exponential function and depends on several factors, and there is a shunt resistance and there is a series resistance. Okay. So series resistance is basically a representation of the ohmic losses. The ohmic losses or contact losses that is involved in the solar PV panel. Okay. And the RSH, that is the shunt resistance, that is also a representation of the leakage current that pass through the solar PV panel. Okay. And the ISH is the that leakage current. Okay. To represent the leakage current through that solar PV panel, we represent it as in terms of parallel branch. Okay. So all of you know Kirchhoff's current law, right? Kirchhoff's current law. So equation 1 satisfies the Kirchhoff current law, right? So your output current IPV becomes IL minus ID minus ISH. Okay. And that ID expression is given here. So that is the output current IPV what you get. Now if you want to know the shunt leakage current, that you can model it as a V plus IRS by RSH. Okay. And that photocurrent expression also is temperature dependent. Okay. Because as I told, temperature and conductance, irradiation. So G is the irradiation parameter and the temperature you see Tc minus Tc reference. Okay. And Kf is the short circuit current temperature coefficient. Okay. And IAC is the short circuit current. So that photocurrent, if you see, that is what I say when a solar PV solar cells PV cells receive the irradiation and the temperature, that will affect how much photocurrent you generate. Okay. Then the open circuit voltage also is a parameter or is a function of both temperature and irradiance, and you can represent it as B open circuit. So STC is at the standard temperature condition. Okay. So VOC STC plus VT ln G by GST. So wherever you see STC, that is the value at the standard temperature condition. Okay. So now again the how to evaluate the efficiency of PV module. So whatever the power you are getting at the output divided by the radiance and the area of the panel. Okay. So that means whatever power you are getting or the energy you are getting from the solar, you may not get directly as the output. So it depends on many factors as I mentioned, and that is how you calculate the efficiency. Okay. So this is very brief of a analysis of that equivalent circuit of a solar PV model. Got it? So, basically we represent it as a current source. When you go for power electronics and do some kind of system level studies. So, this solar cell we call it as a current source, okay. And mostly if you remember, when you have a solar PV inverter, we model the controller as a grid following basically classically, so that whatever the grid wants, you just inject that current, you do not care of the voltage. So, you just follow the voltage and you inject the amount of current, or if I say in terms of power, the active power, okay. So, mostly it generates the active power, right. So, that is what I gave an example. In that case, somebody wants to model it, circuit model of a solar grid connected solar PV panel, you can use this model, okay. And the topology wise, as I told, you can have several combinations depending upon which application you are using, okay. You can even directly couple the PV, solar PV with the electrolyzer without help of converter. So, that is one of the trending topic nowadays, how to avoid converter for this application, because as I told, hydrogen electrolyzer is a high cost concern involved in that, right. So, in that again, if you add power electronic converter for even low power scale, then it does not make sense, your investment cost and the performance you want or you want to give. So, that is why in certain application where your power is not that much high or significant requirement is there, you can simply localized way you can generate direct coupling. And if you see it, as I told, it is simple and cost effective. And of course, here I will tell about MPPT. So, solar power is mostly operates in the mode of called MPPT. MPPT is called maximum power point tracking, okay. So, what we do, I showed you the current and voltage expression of the solar PV in my previous equations, right. So, if you draw a curve between VPV, IPV, but particularly they call it open circuit voltage and short circuit current, and then you draw also the output power what you saw, which is generated from the solar PV. So, the power that is generated from the solar PV and you try to plot that against the open circuit voltage, you will see the curve starts from 0, goes to a maximum point and then falls to the again 0 power. So, in very classical way, nowadays several modifications are there, because you do not want your solar PV to operate always maximum power point tracking, but the classical way you always try, because as I told, it increases and then falls. So, there is a peak point, right. So, the peak point means that peak point refers to the maximum power, the y axis is power and the x axis is voltage. So, that peak point corresponds to the maximum power, and the voltage, that voltage you want to always maintain, because the moment you change the voltage here and there, the power point tracking will drop, so that you will not get enough output power, okay. So, that is why how people do that, there are different methods I will tell in the next slide. So, either you directly control them or you control through some kind of DC-DC interface after the output of the solar PV. So, maybe what I told, like if my solar MPPT curve I want to maintain, I want to basically maintain a voltage, right. So, that voltage I want to control, and that through that control I want to switch some DC-DC boost converter. That is what you can do. So, anytime voltage try to go down, you try to make it up. For that, your current will be automatically adjusted, so that you maintain your MPPT point. Okay. That is one way, or there are other methods are there where you can also use. That is directly coupling, but again DC coupled system. Okay. DC coupled system, from the name you know, you do not need any kind of AC conversion, AC to DC conversion. So, as I told, second point already I told. So, incorporate DC-DC converter to enable MPPT. Okay. So, the DC-DC converter, if you remember yesterday we are trying to control, of course it is for electrolyzer, but we are trying, I showed you how to control the output voltage of a DC-DC converter, right. So, same DC-DC converter, the reference you are giving, you remember that reference 262 whatever some application I told, that reference you can put that voltage corresponds to the MPPT point. So, anytime you change your system condition, it will try to track that reference voltage. If you can achieve that reference voltage, at that voltage you will maintain that maximum power point. So, that you will, so through that voltage control you try to control the DC-DC boost converter. So, it will make sure that output of the DC-DC converter you maintain the maximum power and you can utilize whatever you want to utilize. Okay. So, and also it improves efficiency and operational flexibility. Okay. Now, another wave coupled system, as I am telling, AC coupled system. So, AC coupled comes when you want some kind of grid integration, or maybe what we discussed in the previous lecture, wind energy system fed electrolyzer, because wind energy generate AC. Okay. Definitely, if you want to, even if you generate hydrogen locally also, you need to convert to DC. But even at grid scale where you have batteries or solar, wind, and suddenly you want to have a electrolyzer in between. So, you will take the common bus, you will connect a electrolyzer at a common AC bus, which you can say may be the point of common coupling, where all other sources will be connected. So, that point of common coupling power becomes AC, because it is connected to the grid. So, that AC you bring and to the downscale you make it to AC to DC, and then after AC to DC also, if the voltage level is not okay, you might end up with using another DC-DC buck converter for the electrolyzer use. So, it enables energy storage, continuous operation and better control. Okay. So, because as I told, this AC coupled system makes more sense when you build the system at a higher scale, let us say community microgrid, or particularly when I say grid connected systems. So, there we call hydrogen at scale. So, there will be not single electrolyzer, there will be multiple electrolyzers that combinedly generating the amount of power at the grid level. Okay. So, that is about the three, basically the three topologies available in the literature, and yeah. So, this is one those pictures only, like you can, if this is a directly coupling, you can, is of course very high level schematic, but there are technology involved how to maintain this. So, the paper I provided, you can go through that and to know more how the operation happens. Okay. This is a directly coupled. If you have a DC bus system, then you will have a DC-DC converter. Sometimes the storage system is optional. If you can have a storage, it is okay. Storage means battery, kind of battery energy storage, and if you have that, you can, because what happens, hydrogen production, if you directly taking from solar power is not available at night. So, hydrogen production will be stopped. So, that time battery can be backup. But having said that, if you can imagine how much cost is also involved here. Battery is not a small cost, right. So, hydrogen even cost not small cost. So, depending upon whether you require hydrogen production at the night, you have an objective there, then it makes sense you make a storage system available that can capture the solar power in the daytime in the form of charging, and the night time in form of discharging, it can supply power. So, that part you can disconnect, solar power is not available, power will flow from storage to electrolyzer, and that you can utilize for hydrogen production through discharging of the battery. But that is if conditional, if it is required. Okay. So, that is again DC coupling. Now, for AC coupling, as I told, you see that power system. That power system basically the grid connected system. There will be several other sources, loads will be connected, and there will be a bus, AC bus, from where you all the resources, if you have a wind, solar, storage, electrolyzer, you take as your connection points, and depending upon what is your required supply, you either use directly those power or you convert to AC to DC. So, that power system again will be not small. So, then in that scale the electrolyzer capacity also will be very big. Solar PV will be not like a rooftop solar, it will be a big solar power for solar plant. Storage also will be adequate depending upon the demand requirement. Okay. So, in that case also you can also expect some kind of ancillary services, which we will discuss tomorrow. I will also tell you from the electrolyzer itself. So, here I want to give an example before I start. So, as I told you, if you want to give some grid services, let us say frequency ancillary services, okay, and in mostly frequency in transmission line is related to active power, right, all of you know, right, and voltage is controlled by reactive power, transmission level I am saying, and most of our Indian grid is transmission level I am talking about. So, if a solar individually has to give some frequency ancillary services and suddenly under frequency happens, solar is already at MPPT. So, frequency active power is related through some droop characteristics. Droop means they are not directly related. So, if you are, it is like a droop, you can say inversely related type. Okay. So, if under frequency happens, so grid expect the solar power, it will give some active power, because frequency drops, you give some more active power. But if you already maintain your MPPT, you do not have any capacity to give that active power, right. So, that is why what nowadays utility operator is asking, you come up the solar PV inverter design, so that you always have a capacity of 15%, 20% extra to your rating, okay, and you make sure you also have the capability to run at a minimum power to your MPPT. So, MPPT point, as I told in the top point, right, suddenly if my MPPT point drops, but my capacity is MPPT, but I run at lower power. So, I will have some power reserve capacity, right. So, at that power reserve capacity also you should be able to operate. So, that frequency drops, that power you can give to the grid, and of course, as professor was telling, this all are tariff based. So, utility operator will give you some kind of benefit, some kind of benefits for providing these services. But the interesting why I am telling, that is one thing you can get, but another disadvantage, the moment you drop from the MPPT, your expected power you cannot generate. So, your solar investment what you did for 100% to run at 100% power rating always, but once you are dropping, you are not generating the expected power every day, right. So, to mitigate that, this hydrogen can help the solar power. So, what will happen, solar power will make it MPPT, hydrogen will do that job of controlling its active power based on the frequency. That is why we call it as a flexible load, not a simple passive load, R load or inductive load. So, it will help to maintain the solar at MPPT, but when frequency event happens, it will give the active power, because this electrolyzer will not be required to operate always at 100% capacity. It can operate between 30, 50%, 60% depending upon how much hydrogen. You will definitely not require hydrogen production 24/7, right. So, you can if your hydrogen production or hydrogen demand is less, you definitely drop down your power consumption capacity, and when it is required you can again increase. So, that kind of demand flexibility this hydrogen brings into the grid. That is the whole objective of this workshop or the 5-day program. At grid scale, this hydrogen electrolyzer can be a good, I can say in layman's language, good friend for renewables. Being a load, it can support the grid, because renewables are basically generating sources, right. Being a load, being a flexible load, and when I say flexible, basically demand flexibility. Like grid demand more power, it can give, grid demand less power, it can reduce the power. So, it will not hamper the power generation from the renewables. Okay. So, that is the another important. So, basically what are those services, I will tell in my lecture next, when I will talk about some kind of grid code standards for this IBS. Okay. So, you can see, I mean, I have taken something from the literature. So, it is generic. So, as I told, PV power generation is not smooth like synchronous power, right. PV is highly dependent on weather. So, temperature changes, power will change, and temperature, if you see your morning to evening temperature profile highly fluctuate, right. Even Dharwad is, you can see every 15 minutes you do not see, you cannot predict whether it will be raining or it will be sunny. So, in that perspective, once this profile of temperature irradiance change, then our power output will definitely change, and that power and output changes, that will impact, because you are feeding that power to the electrolyzer. So, electrolyzer input power will highly fluctuate. So, due to that fluctuation, electrolyzer membranes, that may undergo some kind of degradation, or some kind of any kind of abnormality can happen, because the power keeps on fluctuates if directly fed from solar. But what is the solution? If you are kind of a DC-DC power converter, you try to maintain that through MPPT. Through voltage control, you whatever power fluctuate, voltage fluctuate, you bring into MPPT. So, that hydrogen do not see that much power fluctuation once you have this MPPT controller. Then also it improves system performance during fluctuation. Partial shedding is one kind, right. Partial shedding, all of you know, right. So, the PV panel, some PV panels are sometimes, if you have seen somewhere, it is inclined, right. So, when the sun goes from east to west, and all sometimes you have cloudy environment, or some kind of, I mean, your total panel is not getting the proper intensity. Some part is getting full intensity, some part will get uneven intensity distribution over the panel. That you can say some kind of partial shedding impact. That will also affect the output power. Okay. But in that case, if you have this MPPT control, and you can ensure that the maximum power point you can maintain through some kind of control philosophy, then it makes sense, and your hydrogen production will not be impacted that much. So, MPPT control method, there are so many, starting from the traditional to the upcoming technology. Even this machine learning algorithms also people are using. There are some example I have put. The traditional is perturb observe algorithm, P and O. INC stands for, so the previous paper I showed you, that you can open and see each of the techniques. So, basically they are using different kind of genetic algorithm or machine learning techniques to maintain that MPPT point. Okay. So, different intelligence techniques have their own objective, based on, basically they are like their own mathematics. So, who are from machine learning background, these are same philosophy, but its application is how to maintain the MPPT here. So, particle swarm optimization, different optimization based techniques are also available, genetic algorithm. Then intelligent means fuzzy logic, artificial neural network, and hybrid. Sometimes you traditional method you put in close with the intelligent techniques. So, you do not want to the classically doing the control, MPPT control, you attach the machine learning technique. So, it will make it automatic and more intelligent controller. Okay. So, these are some of the classification. This is already I told, no need to discuss what are the types of DC-DC you can use, isolated, non-isolated. And this is also the requirement for power electronic inverters, power electronic converters. This is also we discussed when we were discussing DC-DC and AC-DC. So, one of the as we have less time, I will say you only one case study. It is in Australia. So, they have a 2 megawatt solar PV power plant. Okay. And to that a 1.044 megawatt PEM electrolyzer, polyelectrolyte membrane electrolyzer is connected. Along with that, there is a 200 ampere battery energy storage also system is connected. And this electrolyzer of 1.044 is not a single electrolyzer. There are 6 PEM electrolyzer connected in parallel, generating total power of 1.044 megawatt. So, what is the power of each electrolyzer? 6 are generating 1.044. So, what is the power of each? By 6, right? A parallel combination I am telling. Now, the question is, this case study says how to coordinately operate between these 5 electrolyzer. Let us say one power demand comes, not to overload any of the electrolyzer beyond their capacity. So, coordinately operating these 5 parallel connected electrolyzers. So, this is about that case study. So, the structure looks like this. So, you can see the right side electrolyzer 1, unit 1 to 6, all are identical, and power rating also, the power electronics point of view also they are equal, and in the left side you have a battery storage and you have a solar PV inverter systems. Okay, this is their total system architecture, you can say. Okay. So, they call it industrial green hydrogen production hub. Okay. So, details you will find in this paper also. So, what is the problem statement? Because renewable energy, as I told, they feel that it is intermittent and highly power fluctuates. So, that fluctuating power, if you do not coordinate this electrolyzer properly, they might directly impact the hydrogen production or sometimes damage the hydrogen electrolyzer, because they have to do because parallel electrolyzer you have to coordinately operate, means each electrolyzer with some kind of protection strategy, right, because power electronics are involved. If you see in the model, power electronics are involved, like buck converter, single stage buck. So, once this power, because let us say one electrolyzer have a maximum limit or lower limit. So, the protection scheme works like if you hit the limit, you switch off, right. That means, if the power fluctuates too much, then it will directly hit the limit of each electrolyzer capacity, upper or lower, sometimes it is higher or sometimes lower due to low power requirement. So, this electrolyzer or including the power electronic has to be switch on and switch off frequently, and that frequent switching and off, on and off, will directly affect the membrane or the electrolyzer electrodes and all. What they observed? That is why in this there is a standard on and off technique which they call choppy control. So, that face this kind of issue, because they only set the upper and lower limit for each of the electrolyzer, and once they, due to high solar PV fluctuation, these limits, upper and lower limits of the electrolyzer frequently hit, and the electrolyzer keeps on switching on and off every time. It is a load, right. It is like R load, you switch on, switch off, RL load, you switch, like electrolyzer itself a load. There is a breaker, if you see in the model, there are breakers are there, right, switch 1 to switch 6. So, those switches are keep on and off, that means that is the input of buck converter, right. So, due to that the hydrogen production becomes impacted. So, they told that they will come up with a robust power coordination technology. Okay. And how they did this? So, this is I was telling about the MPPT curve, whoever do not know. So, the curve says the x axis is the voltage and the y axis in the power. So, the peak point of that valley you basically call the maximum power point tracking, and if you can see this kilowatt per meter square is what I told, irradiance, right. So, that irradiance itself directly affect how much maximum power you can generate. Also it varies on the temperature, but not shown here. So, PV characteristics, this is their what they studied. So, this is their electrolyzer model, already we discussed, I think, right. Remember or forget? Tomorrow is the exam, right? Okay. So, please go through. This is the dynamic electrical equivalent model, right. Then what is their methodology? So, first they model the PV, then electrolyzer, then some storage, and this is like different design thing they did step by step. Then what they did, sorry, the first graph, is basically there is a slow variation and high variation. Okay. So, due to that how much the solar power is keeps on changing, depending on that the electrolyzer power input also keeps on changing. Okay. So, that change this they put two variation, one is very fast variation, one is very slow variation. And what they did, as I was telling, the classical existing what is choppy control, they call start stop, like initial frequent start and stop. But what they told, that instead of giving a single lower limit higher limit, make it different zones. Okay. So, you switch between different zones between lower and higher, so that you need not to be every time switch on and off. So, what I mean, so let us say my electrolyzer is 100 megawatt. So, I keep my lower limit as 10 megawatt and 90 megawatt. That is the startup control. If the power fluctuation above 90 megawatt, I will tell switch off, or power below 10 megawatt, I will tell switch off. Instead of doing that, I will put 3 layer in between, 10 to 30, 30 to 50, 50 to 90, and I will operate, let us say, at when there is a no requirement, operate in the low zone. And once the solar goes up, power will come up, power consumption requirement is up, then you slowly very smoothly change between different zones, so that you need not to directly wait for high power then switch off. Okay. So, that is the thing they brought here. So, they divided into low, high and overload. So, this is that conventional choppy. So, depending upon you can follow that paper reference 4, of course. So, depending on one electrolyzer, you see their power rating, the expected power and their rating, you match. If they below minimum and above maximum, you trip them. But instead of this, the segmented choppy is like, as I told, there are different segments. So, it is basically a logic, if else logic, nothing else. So, this logic they implemented in terms of different segments, high, low and the overload conditions, and they run that. And if you see, this is the result of a choppy control. If you see, the red and green are overlapped. Okay. So, the red is the reference power signal for a electrolyzer, and the dotted green are the power consumption. So, this is as it is like a there is very classical choppy control. If you see, the solar power is changing, the red color signal also changing, because the more power you generate, more you have to consume, right. And due to the power controller, this red color is also following that, and you can see there are very big steps the electrolyzer is facing in terms of power, and that due to that it is also going through that switch on and off condition. And in comparison to, if I see the segmented one, so if you see, the one operating zone to other operating zone is not a step, it is a smooth one, because it has passed through different layers within the low and high. Okay. So, that is why they achieved this. They told that with this segmented power coordination control, they achieve a better smooth power coordination among the hydrogen electrolyzer, and that they enhances the reliability of their hydrogen production. There are other results are there, but I will skip that, we are already time. Yeah, so I want to say that this segmented control there improved the system reliability and hydrogen yield, hydrogen production. And of course, this is one of the case study I showed, but at least you understand what are the system architecture, what are the things required, and what could be it. Your study can be at the device level, your study can be at the system integration level. So, depending upon that, your objectives, you can work on various aspects. Okay. Thank you.
Topologies, DC coupled system and AC coupled system. Out of that, in AC coupled system, it allows the integration with the grid, and for DC, it is for the efficiency and enables MPPT. So, which one should we choose if we want to integrate? Means DC, what is the advantage if we want to use it in the grid part?
No, definitely DC has more advantage, because some of the generation are AC and our loads are AC. We are still for grid integration, our grid itself AC. So, as I told, different architecture, those are highly subjected to your objective. Let us say you are just for hydrogen production for some end uses, you want to generate locally in the form of, let us say, kilowatt or maybe less than kilowatt. So, that time you can go with a DC-DC, because at the end of the day electrolysis happens with a DC power supply. So, but if you are aiming for a big investment at the grid scale and you want to integrate to the AC grid, definitely you go for AC coupled, because you cannot pass the DC power or consume DC power directly from the AC grid. So, you have to have some kind of conversion in between. Yes.
You mentioned about hydrogen storage electrolyzer being a flexible load. So, does it mean that it starts feeding power back to the grid, or it reduces the output? What did you mean there?
Okay, so flexible load is basically considered as a load. So, load means it is only sink of active power. So, but that sink is not fixed. So, that sink you can, because you have power electronics and control involved, that sink you can make it a relation to the frequency services. Let us say I am giving a, I have a AC/DC rectifier, active front end rectifier. I want to control it as a grid following or firming. So, from there I can control my active power consumption based on the grid frequency. But of course, its counterpart is called a fuel cell. So, that hydrogen what you produce, you can back it, make it inject to the grid through a fuel cell, where you give hydrogen as an input, then it is like exactly opposite operation of hydrogen. And there are certain technology are available which we call reversible electrolyzer, where you can do both electrolysis and fuel cell operation in a single cell. So, but here of course, grid ancillary service I told in meaning to the flexible load, meaning to the sink of active power. That is how you can give some service to the grid.
How if we have a solar just a battery for storage, or other ways to have hydrogen electrolyzer, in the end both of them have DC port as the interface to the outside world. How does the control and this operation changes when we bring a hydrogen electrolyzer into the picture compared to if you simply treat it as a battery?
Yes, so the one I will again repeat that PQ curve. So, if I draw my P active power and reactive power axis. So, as I told, electrolyzer can operate being a sink of active power, but it can source both reactive and source and sink both reactive power. But for a battery, as we know, it is a bidirectional device, it can operate in all four quadrants. That is one of the system characteristics. Another important characteristic is hydrogen electrolyzer is a low voltage high current device, but I think battery you can still operate with a normal DC voltage. So, even if they share the same DC bus which is compatible with battery, you might require another stage of DC-DC step down to feed the electrolyzer. Yeah. Thank you.